Bismillahirrahmanirrahim. Welcome everybody. Today we are going to start the third lecture of the chapter solids, and that is the properties of crystalline solids. This one is a very important lecture. So kindly watch it completely and very attentively in order to have a complete concept of all properties of the crystalline solids. And if you have not subscribed my channel so far, subscribe it and show your support please. So let us start the topic now. The first property of the crystalline solids is the geometrical shape. Every crystalline solid has a specific geometric shape. When I say it has specific geometric shape, it means it has specific interfacial angles. I have explained the concept of the interfacial angles in my lecture number 2 of the solids. So the consistency of interfacial angles is an essential characteristic of crystalline solid. Mean a particular crystalline solid has specific interfacial angles and the faces intersect each other at these specific angles. Now these angles may vary from solid to solid, but in case of a particular solid, all interfacial angles they remain same. Even if you grind a crystalline solid to the powder form, even then there will be no difference in the interfacial angles. So the interfacial angle remains same in a particular crystalline solid. Every crystalline solid has a definite geometric shape that remains same. I have given an example of the two crystals. Suppose that these crystals are grown and this one is a perfect crystal while this one is a rapidly grown crystal. Mean this crystal was grown in the short duration of time, very fastly, very rapidly. So both crystals they have different size. Both crystals their shape is almost same, their size is different, but still the interfacial angle in both these crystals that is same. It means whether you will grow a crystal in a slow manner or in a fast manner, their shape, their size that may slightly change, but there will be no difference in the interfacial angles. Interfacial angles remain the same. So this one was the first property, which means that every crystalline solid has definite geometric shapes. Now let us move towards the second point, which is every crystalline solid has a sharp or definite melting point. And these sharp or definite melting points can be used to identify the crystalline solid. For example, the melting point of the sodium chloride, that is 801, and this one is a sharp, a specific, a definite melting point of NaCl. So NaCl can be identified with the help of its melting point. And this definite melting point is because of the regular arrangement of the particles in the crystalline solids. Third one is the cleavage planes. Cleavage planes are the areas where the structure of crystal is weakest. So these are the areas where the crystal structure is weakest and you can easily break or cut the crystal into pieces at this particular point. It is the only along these planes that a crystalline solid can be cut or a crystal can be cut. So you cannot cut any crystal at any point of your own desire. But there are some points where the crystal is the weakest in its structure. So you can cut the crystals from these points and these are called as the cleavage planes. For example, suppose that this one is the structure of a hypothetical crystal. Now this one is the cleavage plane. This will be the weakest area from where this crystal can be cut. And you cannot cut this crystal along this plane because in this direction the crystal is not weakest. So it means cleavage planes are the specific planes from where the crystals can be easily cut. And I have shown the cleavage planes in a cube like this. This one is a plane, this one is a cleavage plane, and like the vertical planes are there. Now cleavage is an anisotropic property. What is meant by the anisotropic property and what is anisotropy? Let us discuss it now. What is anisotropy? Actually, every amorphous solid is isotropic in nature. Isotropic in nature, which means that the intensity of the physical properties remains same in all the directions. If you will change the direction, there will be no difference in the intensity of the physical properties in case of amorphous solids. Why? Because changing the direction does not matter at all. In every direction in an amorphous solid, the particles are randomly arranged. So changing the direction will not matter because in every direction the particles are randomly arranged. So if you will change the direction, that will not have any impact on the physical properties. But in case of a crystalline solid, changing the direction may affect the intensity of the physical properties. And the phenomena in which changing the direction affects the intensity of the physical properties is called as anisotropy. And a property which shows anisotropy is called as anisotropic property. Now the concept of anisotropy is because of the particular arrangement of the particles in case of a crystal. Now what are the examples of the anisotropic properties? Thermal and electrical conductivity is an example. Coefficient of thermal expansion, refractive index. Not all the properties are anisotropic in nature, but there are some specific properties which show anisotropy. Like melting point will not show anisotropy, that you will change the direction and the melting point will be changed. It is not something like that. So these are the examples of some anisotropic properties. Now I have illustrated it with help of a diagram. Let's suppose that a property is studied in this direction AB and the same property is studied in this direction CD. Now you can see that when you are studying a property in the direction AB, it is having only one type of the particles. It is facing only one type of the particles. But when you will study the same property in this direction, it is facing two types of the particles. So because of the difference in the arrangement of the particles, the anisotropy is shown, or the intensity of the physical properties is changed, and this phenomena is called as the anisotropy, which is a characteristic feature of the crystalline solids only, while amorphous solids, they just show the isotropic behavior. Cleavage is an example of an isotropic property. In case of graphite, graphite has a layered structure, and parallel to the layers, graphite is conductor because there are spaces between the layers through which the electrons can easily move. But when you see perpendicular to the layers, free electrons are available, but there is no space for their movement, so graphite is non-conductor. So parallel to the layers, it is conductor. Perpendicular to the layers, it is non-conductor. It means that changing the direction changes the electrical conductivity. So that is also a best example of the anisotropy. In the same way, the crystals cannot be cut in any direction, in any plane. So if you change the direction, the cleavage planes also change. That is also an anisotropic behavior, and it is also an anisotropic property. Now let us discuss the next property. The fifth one, and that is the habit of crystal. Habit of crystal is actually the specific shape in which a crystal grows. For example, habit of NaCl crystal is cubic. So NaCl crystal grows in the form of a cubic crystal. It is cubic in nature. This one is an NaCl crystal. Unit cell of the NaCl crystal, that is cubic. But if a saturated solution of the NaCl is prepared and you add some impurity in it, suppose that you have added 10% urea in the saturated solution of the NaCl, and now the crystals are grown. Now the habit of crystal, or the shape of the crystal, that will also be changed. And in this particular case now, it will be octahedral. So it will become octahedral now. It means that habit is the particular shape in which a crystal grows, and habit of the crystal can be changed by adding some impurities. Why the habit is changed? Because when NaCl is pure, there are only cations and anions of the sodium chloride. But when the urea is added, the urea molecule will also interfere in the arrangement of the sodium ions and chloride ions. So due to which the habit is changed. This one is the fifth property, that is the habit of the crystal. Now let us move towards the sixth one. It is symmetry. Symmetry is actually the repetition of faces and angles when a crystal is rotated at 360 degree. So if you have a crystal and you rotate it at 360 degree, then the faces, angles, edges, they repeat themselves, and this repetition is called as the symmetry. Now there are certain elements of symmetry. And what are those elements of symmetry? Let us discuss them. Suppose that I am going to draw a cubic unit cell. So there will be a center about which this crystal is rotated, and this is called as the center of symmetry. So the first element is the center of symmetry. Now the second one, there is an axis which passes through this center of symmetry, and this axis is called as the axis of symmetry. And this one is a second element of the symmetry. And now the third one is the plane through which symmetry is seen. Now this plane is actually the plane of symmetry. And it is the third element of symmetry. So what are the elements of the symmetry? The center of symmetry about which a crystal is rotated, and the axis that passes through this center, and the plane of symmetry. These are called as the elements of symmetry. And some books write down that the angle of symmetry is also included in it. So there will be four: center of symmetry, axis of symmetry, plane of symmetry, and angle of symmetry. These four characteristics are collectively called as the elements of symmetry. And this one is the axis about which the crystal is being rotated, and it shows the repetition of the faces and angles. So this was the sixth property. Now let us move towards the next one. Let us discuss the seventh property now. That is isomorphism. Iso mean same, morph mean shape, and ISM usually means system. So isomorphism word means same shape system. There will be same shape of two or more than two different crystalline solids. So if two or more than two different crystalline solids, they show same shape, then this phenomena is called as the isomorphism. Now let us discuss the example of the isomorphism, like sodium fluoride and magnesium oxide. Both are cubic, both have cubic crystals. So these are two different crystalline solids, but they are having same crystal shape. This is called as the isomorphism, and these two are called as the isomorphs of each other. Similarly, there is an example: potassium sulfate and potassium chromate. These are two different crystalline solids, but they have same shape of their crystal, and that is the orthorhombic so they are also called as the isomorphs of each other. Now let us discuss why the isomorphism arises actually. The phenomena of the isomorphism is basically due to the same atomic ratio. Isomorphism arises because the different crystalline solids, they have same atomic ratio, and because of this same atomic ratio, their crystalline shape is also same. For example, in case of the sodium fluoride and magnesium oxide, the atomic ratio is 1:1, and in case of these two isomorphs, the atomic ratio is 2:1:4, means 2 atoms of potassium, 1 atom of sulfur, and 4 atoms of oxygen, and the same is the ratio in this. So isomorphism arises because of the same atomic ratio. Now isomorphs have certain similarities and they have certain dissimilarities. What is their similarity? The similarity is they have same crystalline shape, they have same atomic ratio, and usually they have same shape of their anions. Like in this case, the sulfate ion is tetrahedral, and same is the case of the chromate ion. So both anions, they are having same geometry or same shape. What are the dissimilarities between them? They have different physical and chemical properties. Their physical properties are different because of their different formula, their different molar masses, and their chemical properties are different because of their different electronic configuration of the atoms. So physical and chemical properties, they are different. Now isomorphism is not a concept which is just related to the compounds, but the elements, they also show the isomorphism. For example, gold and silver, both are the coinage metals, and they both have cubic crystals. So these are two different elements, but their crystalline shape is same, and they will also be called as the isomorphs of each other. They will be having different physical and chemical properties, but their crystalline shape will be same. So isomorphism is not a concept which is just related to the compounds, but the elements, they also show the isomorphism. This was the 7th property of the crystalline solid. Now let us move towards the eighth one. I would like to discuss the eighth property in two ways. I will divide it into two parts. One will be the polymorphism, and other one is the allotropy. Now polymorphism means, poly mean many, morph mean shape, and ISM mean system. So it is a phenomena, it is a system in which there are many shapes of one crystalline solid. So in this case, one crystalline solid has many different shapes. That is called as the polymorphism. But the condition is that this crystalline solid should be a compound. And if there is an element showing different crystalline shapes, then this phenomena is called as allotropy. It is not called as the polymorphism. So this one is the concept which is applicable to the compounds, and this one is the same concept for the elements. While in isomorphism, that was applicable to both compounds and elements, but the polymorphism and allotropy, these are different. Polymorphism is a term reserved for the compounds, and allotropy is a term which is reserved for the elements. Now let us discuss some of their examples. Like in case of polymorphism, calcium carbonate is a crystalline solid, and this crystalline solid has two different shapes. Sometimes it exists in the trigonal crystalline shape, and other it shows the orthorhombic shape. Now when calcium carbonate exists in these two different shapes, the compound is same but the crystalline shapes are different, so these are called as the polymorphs of each other. Polymorphs, they have also certain similarities and differences. Now what are their similarities? Their similarities are actually their chemical properties. So their chemical properties are same because the calcium carbonate is a single compound, and the electronic configuration, the bonding, that will remain same in these two different forms, so the chemical properties will be same. And what will be the dissimilarity? So there will be two dissimilarities, one shape, another physical properties. Now why they have different physical properties? Because there is difference in the arrangement of the particles, and the physical properties, they depend upon the arrangement of the particles, so they will be different. Now let us discuss the examples of allotropy. You know that carbon exists in three crystalline forms: graphite, hexagonal, layered structure, diamond, face-centered cubic structure, And similarly, buckyballs that are football shaped and they consist of the pentagonal and hexagonal rings. Now these are three allotropes of the carbon. When you will burn any of these three allotropes, when you will combust them, you will get same product, and that will be carbon dioxide gas. It means that combustion of these three different allotropic forms gives same products, which shows that they have same chemical properties, but they have different physical properties, like graphite is conductor, diamond is insulator, and buckyballs are semiconductors. So their physical properties are different, but their chemical properties they are same. In the same way, sulfur has different allotropic forms, rhombic, monoclinic, and similarly phosphorus exists in the 6 different allotropic forms, out of which 3 are very important and we study in the grade 12, and they are the white, red and black phosphorus. So allotropy is a common phenomena which is seen in the elements, and polymorphism is seen in the compounds. Now because of these two terms, polymorphism and allotropy, a third term arises, and that is the last property of the crystalline solid. It is transition temperature. Transition temperature is a term which is because of these two, polymorphism and allotropy, because transition temperature is the temperature at which two different polymorphic forms of a compound or different allotropic forms of an element, they coexist at the state of dynamic equilibrium. If a compound has no different shapes, or if an element has no different shapes, there will be no phenomena of polymorphism, no phenomena of allotropy, then there will be no concept of their coexistence at the dynamic equilibrium, so there will be no concept of the transition temperature at all. And transition temperature is always less than melting point of the crystalline solid, because at melting point the crystalline solid will melt, it will not be in the solid state anymore, so it should be less than the melting point. Now let us discuss some example. Like sulfur, it exists in the rhombic, as well as it exists in the monoclinic form. And what is the temperature for it? 95.5 degrees. This 95.5 degrees is the transition temperature of the sulfur, where the two different crystalline forms, rhombic and monoclinic form, they coexist at the state of dynamic equilibrium. Listen very carefully now. If we will increase the temperature from 95.5 degrees C, it means that the conversion of rhombic sulfur to monoclinic will be increased. I will make it easier. If you increase the temperature from transition temperature, the conversion is towards right. And if the temperature will be decreased from 95.5 degrees C, then there will be more conversion of monoclinic sulfur into the rhombic sulfur. Mean when the transition temperature is decreased, the backward, or you can say the reaction in the left dominates. That's why we say that below 95.5 degrees C, sulfur exists only in the rhombic form. And room temperature is 25 degrees C, which is much lesser than 95.5 degrees C. It means at room temperature, which form of the sulfur is seen? That is the rhombic sulfur. So this was the concept of the transition temperature, and these are all the properties of the crystalline solids. I am going to just revise them in 1 minute or less than 1 minute. First, they have definite geometric shape. Their interfacial angles remain same in any case. Second, they have definite or sharp melting points which are used for their identification. Third, crystals can be cut at their weakest points, at their weakest areas, and these planes are called as the cleavage planes. Fourth, crystalline solids show difference in their physical properties in different directions. This is called as anisotropy, and the properties which show anisotropy are called as the anisotropic properties. Fifth, the shape in which the crystal grows, that is called as the habit of the crystal. And habit can be changed by adding the impurities. Like NaCl is cubic in the normal case and it is octahedral when 10% uric is added. Sixth, crystals show repetition of the faces and angles in such a way that you cannot distinguish between the faces. All the faces will seem identical, and this repetition of faces, angles, or edges when a crystal is rotated at 360 degrees C, that is called as the symmetry. There are four elements of symmetry: center of symmetry, axis of symmetry, plane of symmetry, and angle of symmetry. Now, if the different crystalline solids exist in same crystalline shape, that is called as isomorphism, and if one compound shows different crystalline forms, that is polymorphism, and if one element shows different crystalline forms, that is called as allotropy, and if the two different polymorphic forms or two different allotropic forms exist at dynamic equilibrium at a particular temperature, that is called as the transition temperature, which is always lesser than the melting point of the crystalline solid. I have revised these properties for you people. It was all about the third lecture of the solids. Next time, inshallah, we will come up with the classification of the solids depending upon the nature of the bonding. Till then, take care. Allah Hafiz.